So
Okay.
can you just walk me through what a real-time hyperspectral camera is?
The point we use real time is because we can do the hyperspectral camera in the speed like 30 frames per second, which is, I have to say, 1,000 times more faster than the conventional cameras like this. So current commercial cameras do a single image for about 1 minute because that's hyperspectral. You need some mechanical system to move around, to scan the scene, do everything. So it's slow. You need some system streamline to do it. We don't need. Every processing in our device is done by this 200 nanometer array. That is a Metasurface encoder, which can just do everything at the speed of light. As light passes through it, everything's done. So like the dimensionality reduction is instantly done by passing your light through it. So in this case, it's definitely like 1,000 times faster than the conventional ones.
Yeah. How does a hyperspectral camera work in general?
So for example, you have your eyes, you have your iPhone cameras. What they do is they capture 3 different RGB values, right? Those values are acquired by integration of the spectral domain, because your eyes can only get discrete values. So we have, if you don't know, we have 3 cone cells in our eyes, and they can just have different activation stages, and the information gets to your brain, you know what the color is. But after all, they are just discrete values of RGB. So basically, some very interesting information could be just ignored during the process. For example, if I have a spectra, this axis is wavelength, this axis is the intensity, okay? And for example, I have a beam light. The light will be like, okay, for like this is the blue region, I have a peak, okay? A yellow region, I have a curve, I have a valley or something. It's like this. It's resonating. But all these informations, your eyes could have only 3 discrete points, and the points sometimes is like they're useful enough because we live it for 1,000 years, right? But sometimes for some specific task, it's not enough. So with hyperspectral, we can have more than 200. That's a very usual specification. 200 bands of different wavelengths, and like have a lot more information about this.
So for the application that you have, it's detecting real versus fake fruits. And so by breaking it up into like more discrete, different bands of what we're already visually able to see, it's able to I guess see where humans can.
The reason that human eyes fails on this is we see them all the same, because that's the functionality of integration. The information is just discrete values, while if we do the spectra, we have a continuous curve. And with that curve, you just simply compare the curves. Are they different? Are they so different? How many peaks they have? How many absorption values they have? You easily get the results. Sometimes it's even label-free.
So in your research, the main thing that you developed was this encoder here that can sit between the lenses of the camera?
Yes, we directly attach the surface on the sensors chip, just to remove the glass and put it on, and do some alignments, make sure every pixel is aligned, and that's it.
Okay. And so is the sensor, is it an RGB sensor? Or is it a monochrome sensor?
Monochrome sensor, because actually every sensor is all monochrome.
Okay.
RGB sensor is not a sensor, it's a monochrome sensor at a Bayer array. I don't know if you know what's Bayer array. It's just an array, do the exact thing as us. They have RGB filters, and do the calibration. The filters could correspond to a specific sensor pixel, and they do some denormalization on that to get actual intensity. So more or less the sensors are all the same. Absorption lights, and they get the voltage, and that's it. Photo receiver, basically. Photon receiver.
Got it.
So, which means any industrial cameras you can buy online on the market, we can modify it. But we have our own choices, but in theory, everything we can modify to hyperspectral image.
Yeah.
Just by our fabrication.
So when you actually view the video that's coming out of the hyperspectral camera, how does that look compared to an RGB?
It will be just like this, because we cannot really present 200 channels at the same time. So the video, I mean, if it's presented, it's just the image moving. Because it's just like a grayscale. That actually in processing is stacked layers, right? You can only see it very normally because I don't know how to exactly present it, because it's too many information. Human eyes cannot do that. But if you want, I can just get a screen, get different regions, and every region is a single band like this. a very big area, but no.
And so like also the amount of data that's coming off of this, because now does it need to be encoded in a special way because it's got so many more?
It is. That's encoded. So we encode everything here. We get an image tensor. So this thing is like an extracted feature by CNN, as you can imagine. So basically, this thing is a feature map. And as you know, a pre-trained network give us the feature map. And the feature map can be used for classification, segmentation, any other thing you can imagine. So the only data we need to transmit is this one, and which is very low, just 9 channels, which is only 3 times more than the RGB. It's not that much. We transfer it with the normal cables, and into our processor network, they reconstruct. And it's from here this thing goes to 200 bands or something. But all the transmission, all the processing is just 9 bands.
And so for the first application that you did like fake versus real fruits.
Yes.
What are some other applications that?
The possible ones could be way more. As you can see from here, the current like hotspot is from medical world. It's not our study, but from some other groups in the world. They're doing the melanoma detection. So you know melanoma, they have different stages, right? Like sometimes it's severe, sometimes okay, it's just a little bit problem. You can already see it by hand. You have to do the biological analysis. But with hyperspectral, they already discovered that different stage of melanoma or different, if it's just a good one or really bad one, they have different reflection curves. And by doing the hyperspectral scanning, they can directly distinguish the stages and severity by the camera. You don't need to actually penetrate your skin and get your samples in this case. And other things like we basically detect the chemicals, explosions or drugs, because the chemical bonds have different reflection and absorption. Once you have them, you have the characteristic. You do the hyperspectral image.
So there's already a lot of like images available for, let's say, an RGB of melanoma.
Yes.
But what we don't have a lot of data on in this specific example would be like the hyperspectral image of melanoma. So that's something that you need to be able to like get a lot of training data on.
Yeah, we have to like collaborate using the the cameras, hyperspectral cameras to get ground truth. We have to create the data set from scratch. It's not really that easy in this case.
Awesome. Thank you.
No problem.